Hi, I am Sushma, working as a assistant professor in the Department of ECE in Institute of Aeronautical Engineering College. In this session, we are going to discuss about the problems on multiplexer. So, multiplexer is also known as universal logic circuit. So, with this multiplexer, we can implement any boolean function and any logic gates by using multiplexer. So, in this session, we are going to discuss about the implementation of boolean function using multiplexer, implementation of logic gates using multiplexer, and full adder using multiplexer. So, here in the first type, the problems on multiplexer are, so here in first step, here it is this the first step is to select the multiplexer. So if the given expression has n variables, then determine the multiplexer using the formula 2 to the power of n=1. So already we know what is multiplexer. So multiplexer consists of 2 power n inputs and 1 output. So the number of inputs for the multiplexer are 2 power n inputs and 1 output, that is f. Suppose anything that is 1 output. The n indicates 2 to the power of n. In n indicates number of selection lines. So here we have n selection lines in multiplexer. Okay. So it is also known as data selector or data distributor. So any one of the input will be switched to the output in the multiplexer. So if we want to implement any boolean function using multiplexer, first we have to know which multiplexer we have to select. Okay, which 8 by 1 multiplexer or 4 by 1 multiplexer or 2 by 1 multiplexer. We have to select the multiplexer. Then if the given expression has n variables, then determine the multiplexer using the 2 to the power of n=1. Connect the inputs that correspond to the given minterms to logic 1. So, for example, if suppose if function has sigma 2, 3, 6, 7. Okay, the boolean function f indicates sigma 2, 3, 6, 7. So, we have to connect this 2, 3, 6, 7 to the logic 1 and remaining minterms to the logic 0. So, connect all the other inputs to the ground 0, whatever not there in this SOP, the minterms, we have to connect them to the logic 0. So, connect the input variables as the selection lines. For example, if we observe this problem, here implement the boolean function f of a comma b comma c equals sigma m 2, 3, 6, 7 using a multiplexer. So, here first if we write the truth table, a, b, c are inputs and f is output. So, here we have 3 inputs. We will get the 8 combinations 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So, if we have 3 inputs, we have 8 input combinations. So, for that if sigma m 2, 3, 6, 7, that is nothing but the minterms 2, 3, 6, 7, the output is 1. So, 2, 3, 6, 7, the input is 1 and other minterms, the output is 0. So, this is the truth table for the given boolean expression. Okay. So, in this we have the output is 1 for 2, 3, 6, 7. So, for that, here we are implementing 8:1 by using 8:1 multiplexer. So, here we have 3 inputs. So, the selection lines for 2 power n=1. If n number of inputs are there, then here inputs n is equal 3. So, total 2 power 3:1, that is 8:1 multiplexer I am using here. So, 8:1 multiplexer, A, B, C are whatever the inputs are there, take those inputs as selection lines. So, here inputs are A, B, C, connect those inputs as selection lines A, B, C. So, we have to connect the inputs as a selection lines And here for 0 to 7, for 8:1, 8 inputs, 1 output. So 0 to 7 we have. In that, in the Boolean expression, what if it is a SOP, then the minterms are 2, 3, 6, 7. So for this 2, 3, 6, 7, output is 1. So for 2, 3, 6, 7, these are connected to logic 1. And other minterms 0, 1, except 2, 3, 6, 7, other minterms are there. 0, 1, 4, 5 are other minterms. So here for them, we have to connect those to the 0, that is ground. Okay, this is the implementation of Boolean expression using a multiplexer. Here another example, implement the Boolean expression f of a comma b comma c sigma m 0, 1, 3, 5, 7. In this also, here we have A, B, C in our inputs, F is output. So the combinations are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So for this input combination, the output is 1 for 0, 1, 3, 5, 7. So for 0, 1, 3, 5, 7, output is 1. For other minterms, output is 0. Okay. So by observing this truth table, so we have to connect for 0, 1, 3, 5, 7, we have to connect those minterms 0, 1, 3, 5, 7, we have to connect those outputs to the logic 1, and remaining 2, 4, 6. 2, 4, 6 we have to connect to logic 0, that is ground. And the inputs whatever are there, A, B, C, we have to connect A, B, C to as a selection lines. So here we are taking 8 by 1 marks. For that we have 8 input combinations, 3 as selection lines, input selection lines we have to take as ABC as selection lines, and 1 output. In the 8 combination, whatever the minterms expressed in Boolean function, we have to connect the. So here this is the problem on Boolean expression, implementation of Boolean expression using multiplexer. So we have another types of problem. Here we have 3 inputs, total 8 in our input combinations we will get. So here we are using 8 by 1 marks. Directly we can connect the whatever the minterms are there in the Boolean expression, we will connect to the 1, and other whatever not there in this Boolean expression, we will connect that to the 0. So but if we want to implement, suppose if we want to implement the same Boolean expression by using 4 by 1 or 2 by 1 multiplexer, how we have to implement? So that is type 2 problem. Here we here in the type 2, from the given set of n plus 1 input variables, the n least significant variables are used as selection line inputs. So here suppose we have A, B, C for example as input variables. So here in this B and C are used as a here selection lines, and A is used for the input line. Okay. So here for the 2 power n inputs for 2 power n each 1 multiplexer are divided by using an implementation table. So in the implementation table has all the D0, D1, D2, D3 the inputs for multiplexer, under which all the minterms are listed in 2 rows. The first row consists of all minterms where A is complemented, and the second row is remaining minterms where A is uncomplemented form. So we will see the table here. So this is the table. Here if for example f of A comma B comma C is called sigma 2, 3, 6, 7. So we have to implement this Boolean function by using 4:1 multiplexer. So for example here A, B, C are 3 inputs. For 3 inputs we will get the 8 input combination 0, 0, 0, 0, 0, 1 up to 1, 1, 1. So directly by using 8 by 1 multiplexer we can we can connect the minterms whatever present in the boolean expression, we will connect that to the 1, other minterms we will connect to the 0. But if we want to implement this boolean function by using 4:1 multiplexer, we have to apply this implementation table. So in this table, so here in 4:1 multiplexer, we have 4 inputs only. So that I am taking as D0, D1, D2 and D3. Okay. So in first row 1, we have to write the A complement. So A bar we have to write. In second row, we have to write A. And that values we have to write here 0, 1, 2, 3, 4, 5, 6, 7. Okay. So for example, here in this boolean expression, f of a comma b comma c is equal sigma 1, 3, 4, 7 is there. So how to implement this means, here whatever the terms we have 1, 3, 4, 7, we have to make the circle for those values 1, 3, 4, 7. Okay. So if they both, if we have, then we have to observe in the vertical lines here D0, D1, D2 and D3. If the both minterms in the 2 rows are circled, if both minterms here 3 and 7 both are circled means we have to write here 1. Okay. If both are not circled means we have to write here 0. And if both, row 1 is circled and row 2 is not circled, that is A bar complemented is circled and A is not circled, then we have to write A bar. Okay, row 1 is circled means we have to write A bar. If the row 2 is circled and row 1 is not circled means we have to write A. Okay, so these A bar, 0, 1 are the 4 inputs for the 4:1 multiplexer. Okay, so here if both the minterms in 2 rows are circled, 1 is applied to the corresponding multiplexer. So 1 is applied to the multiplexer. If both are not circled, 0 is applied to the corresponding multiplexer input. Okay, if row 1 is circled and row 2 is not circled, and A bar is applied as the input. If row 1 is not circled and row 2 is circled, then A is applied as the input to the multiplexer. So here we will see one example. So f of a comma b comma c sigma m0 to 5, 6 using 4:1 multiplexer. Okay, in this A, B, C, we have 3 input variables. In this 4:1 multiplexer, that is 2 power 2:1, that is 4:1 multiplexer has one output, that is F. So we don't know what are the inputs. Here we have to write the B and C are the selection lines. Another 2 inputs we are take that as selection lines, and we have to know what are the inputs by using implementation table. So in implementation table, write D0, D1, D2 and D3 are the inputs. So D0, D1, D2 and D3 are the inputs. Here in first row, we have to write A bar, and second row we have to write A. So the values 0, 1, 2, 3, 4, 5, 6, 7 we have to write like this. Okay. Then whatever the minterms in the boolean expressions are 0 to 5, 6. So circle those minterms 0 to 5 and 6. Okay. So here we have to observe D0. So D0 in a vertical line here in D0. If A bar is circled and A is not circled, so here we have to write A bar. If A bar is circled, row 1 is circled and row 2 is not circled, we have to write A bar. If row 1 is not circled, row 2 is circled, here we have to write A because A is circled here. Then if both are circled, 2 and 6 both are circled, then we have to write 1. If 3 and 7 both in D3 are not circled, we have to write 0. So these 4 A bar, A1, 0 are the inputs to the 4:1 multiplexer for this boolean expression. So here we have to write A we have to connect here, and A bar to the another input. Here A bar to the first input and A to the second input, and logic 1 to the third input, logic 0 to the fourth input. So A bar and A10 are inputs to the 4:1 multiplexer, and B and C are the selection lines. Okay, this is the implementation of Boolean expression using 4:1 multiplexer. So if we observe the another problem using here, it is a 4-variable Boolean function, f of a, b, c, d, 4-variable Boolean function. So 4-variable Boolean function means we will get the 16 combination, input combination, 0, 0, 0, 0 to up to 1, 1, 1, 0 to 15 we have combinations. So here in the Boolean expression it is expressed as 0, 1, 5, 6, 8, 10, 12, 15. So here we have to implement, but it by using 16:1 multiplexer, it is directly we can connect these minterms to the 1 and other minterms to the 0. But here in this expression we are using 8:1 multiplexer. So for 8:1 multiplexer, A, B, C, D. For 8:1 multiplexer, we have 3 selection lines. So we have to consider B, C, D as selection line. So B, C, D as selection lines. In inputs we have to take as selection lines, and we have to know the inputs by using implementation table. So if for 8:1 multiplexer we have 8 inputs from D0 to D7. In first row we have to write A bar, and second row we have to write A. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 we have to write. Here we have to circle the whatever the minterms are there, we have to circle them in the this implementation table. So here we have to circle 0, 1, 5, 6, 8, 10, 12, 15. Okay. So both are circle means we have to write 1. If row 1 is circle means we have to write A bar. If row 2 is circle means we have to write A. If both are not circle means we have to write 0. In D4, row 2 is circle, so we have wrote A. If row 1 is circle means we have to write A bar. In D6, row 1 is circle, so we have to write A bar. And D7, the row 2 is circle, so we have to write. This is row 1. This is row 2. Okay. So these are the inputs to the multiplexer. So D0 is 1 and D1 is A bar. So here we are getting A bar, and D3 is A bar, and D3 is 0. So it is connected to the ground. So it is 0, and D4 is connected to A. So this is A. And D5 is connected to A bar. So here we are giving A to the NOT gate. So we are getting A bar here. And D6 also connected to the A bar A. So these are the inputs D0 to D7 we have to apply here. So we have to remember, if it is a for n variable, n plus 1 variable multiplexer Boolean expression, n variables, last n variables we have to take as selection lines. Okay. So by using implementation table, we have to know what are the inputs to the multiplexer. So implementation of logic gates using multiplexer. So for example here AND gate is there. So A, B and Y is the output. So if you observe the truth table, A, B, Y, 0, 0, the AND gate function is, if any one of the input is 0, output is 0. So 1, 1, 1. So this is the AND gate. So it is 1 for only 3. So here we are using 2/1 multiplexer. For 4/1 multiplexer, directly we can connect, give it to the D0 to D4, 0, 0, 0, 1. Okay. But I am using here 2/1 mux. So 2/1 mux means 2 inputs, D0 and D1. So 2/1 mux. inputs are D0 and D1 and one output is Y. Okay. So the selection lines here A comma B are inputs. So here I have to take the second B as selection line because 2:1 multiplexer has one selection line and I have to know what are the inputs here. So A bar and A. First row we have to write A bar and second row we have to write A 0, 1, 2, 3. Okay. So here the output is 1 for only 3. Okay. A, B 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 2, 3. So for 3, the minterm 3 we are getting output 1. So we have to circle that 3. And here if both are not circle means we have to take that as 0 input to the multiplexer. And if row 2 is circle, we have to take A. So the 0, A are the input to the multiplexer. If we observe this one, if we observe the truth table functionality, see here, if B is equal 0, the selection line is 0, the first input will be switched to the output. Okay, so B is equal 0. So in these two conditions, the output is 0 because the first input will be switched to the 0. If B is 1, the second input will be switched to the output. So here the second input is A. So A is, if B is 1 means whatever the A is there, that will goes to your output. So 0, 0. If A is 1, that will goes to output. Okay, so it is satisfying the truth table. So the AND gate implementation using 2/1 mux is here 2:1 mux. One input is 0, another input is A, and output is Y. One input is selection B as a selection line. Okay. For example, I want to implement OR gate using multiplexer. Okay. So OR gate A and B and Y. So A, B, Y. A 0, 0, 0, 1, 1, 0, 1, 1. So already we know if any one of the input is 1 to the OR gate, output is 1. So 0, 1, 1, 1. So output is, here we can express Y of A comma B is equal sigma 1, 2, 3. Because for 1, 2, 3, the output is 1. Okay. So by using implementation table, here we are going to implement this OR gate by using D0 and D1, A bar and A 0, 1, 2, 3. So for 1, 2, 3 we have made to circle because the boolean expression will be 1 for 1, 2, 3. Here in D0, if you observe this column, row 2 is circle, that is A is circle. So here we have to write A. If both are circle means we have to write 1. So it is by using 2:1 multiplexer, the output is Y here. Once in A comma B, we have to take second one as selection line B and 2 inputs by using implementation table. One is A and second one is 1. So this is the implementation of logic gate by using multiplexer. So another gates, for example, NAND gate A, B, Y. NAND gate truth table A, B, Y. 0, 0, 0, 1, 1, 0, 1. If any one of the input is 0, output is 1. So this is the truth table of the NAND gate. We can write Y A comma B is equal sigma 0, 1, 2. Okay. So how to implement this by using 2:1 multiplexer? By implementation table, we have to make what are the inputs to the multiplexer. So A bar and A 0, 1, 2, 3. Circle these 0, 1, 2, 3. 0, 1, 2. Okay. If both are circle means we have to write 1. If row 1 is circle means we have to write A bar here. So these are the inputs to the multiplexer 1 and A bar. So here 2:1 multiplexer. So one input we have to take as second input we have to take as selection line. Output is Y and input is 1 and A bar are inputs to the multiplexer. Okay. So another example we will take logic gates of XOR and XNOR gate. So A, B and Y. Okay. A, B by 0 0 0 1 1 0 1 1. So if both inputs are same, we will get the output 0. If both inputs are different, we will get the 1. So here we can write y of a comma b is equal sigma 1 and 2. Okay. So by using implementation table, D0 and D1, A bar and A, 0, 1, 2, 3. So 1 and 2 will be circled here. For D0, row 2 is circled. So here we will write A. This is A bar. So in 2:1 multiply 1 mux, output is Y. And one selection line is we are taking one input B, and A and A bar is A and A bar are the inputs. So A and A bar, that is D0 and D1. Both inputs A and A bar are the inputs. So if you observe the truth table, if B is equal 0, output will be switched to the first input, that is D0. So D0 contain A. So if B is equal 0, whatever the value A is there, that will goes to output. If A is equal 0, Y is equal 0, A is equal 1, Y is equal 1. If B is equal 1, that is selection line is equal 1, then A bar will go to the output. So B is equal to 1, A is 0, so complement value A bar 1 is we are getting output. If A is equal to 1, we are getting A bar, that is 0, we are getting output. So this is true implementation of XOR gate by using 2:1 multiplexer. For XNOR gate, so A, B, this is Y. So D0, D1, A bar, A, 0, 1, 2, 3. For XOR gate, this same truth table, here we will get the A, B, Y, 0, 0, 0, 1, 1, 0, 1, 1. For if the inputs are same, we will get the 1 output, and if inputs are different, we will get the output is 0. So for 0 and 3, we are getting output is 1. So we have to circle them. Here D0, here in this row, A bar is circled. So we are getting A bar. Here we are going to get A. So 2:1 mux. So Y is output, 1 is input is selection line B. And here C, if you A bar, so A not gate, A bar we are getting, A we have to give to the second input. So D0 we are connecting A bar, for D1 we are connecting A. So these are the inputs to the multiplexer. So these are the implementation of logic gates by using 2:1 multiplexer. So implementation of full adder using 4:1 multiplexer. So first we have to write the truth table of full adder. So full adder consists of 3 inputs. A, B, C are the inputs, sum and carry are the outputs. So here by adding 0, 0, 0, we are getting sum 0, carry 0, 0, 0, 1, sum 1, carry 0, 0, 1, 0, 0 plus 1, 1, 1 plus 0, 1. So sum 1, we are not getting any carry. So 0 plus 1, 1, 1 plus 1, we are getting sum 0, carry 1, 1, 0, 0, sum 1, carry 0, 1, 0, 1, sum 1 plus 0, 1, 1 plus 1, we are getting sum 0, carry 1, 1 plus 1, 0 as the 0 is the sum, 1 is carry. Again we are adding 0, so sum is 0, carry is 1. So 1 plus 1 plus 1, we are getting sum is 1, carry is 1. So here first we have to write that here where sum is, where we are getting 1 for the sum for, okay, 1, 2, 4 and 7 we are getting 1. So we have to write the boolean expression for sum, and carry we are getting sigma, where we are getting for 3, 5, 6 and 7. So 3, 5, 6 and 7 we are getting 1. So here we have to, by using implementation table, we have to implement these inputs to the sum and carry. So here 4:1 multiplexer. So we have to take 4 inputs D1, D2, D3. Okay. For sum I am doing here. for some A bar and A, because 4:1 multiplexer, here we have 3 variables. So 2 BC are using as a selection lines. We have to take the input in terms of A. Okay. So here 0, 1, 2, 3, 4, 5, 6, 7. So circle 1, 2 for some 4 and 7. Okay. So in row 2 is circle. So we have to write A. Row 1 is circle. Here we have to write A bar. This is also row 1 A bar. Here A. So these are the inputs to the sum for the 4:1 selection line. For carry, again we have to take the implementation table. So D0, D1, D2 and D3. So this is for carry. A bar and A. 0, 1, 2, 3, 4, 5, 6, 7. So 3, 5, 6, 7. The carry boolean expression is 3, 5, 6, 7. The minterms, whatever there in the carry, 3, 5, 6, 7, we have to make circle them. And if both are not circle, we have to take 0. If row 2 is circle, we have to write A. If both are circle, we have to write 1. So these are the inputs to the carry of the 4:1 multiplexer. So here see A bar, A bar, A are the inputs to the 4:1 multiplexer for this to produce the sum. Okay. So here B and C are the inputs to the selection lines to the both for sum and carry multiplexer. So for S1 and S2 selection lines, for both of them B, C are the inputs. So the B, C are given as a selection lines, and from the implementation table we have got the A bar, A bar, A are the inputs. Here 0, A, 1, we have got the inputs from the implementation table for the carry. So this is the implementation of full adder using 4:1 multiplexer. Here A, B, C are the inputs and sum and carry are the outputs. So for sum and carry we have the separate 4:1 multiplexers, and here B, C are the selection lines, and by using the implementation table we have to know the inputs for the sum and carry. So these are the problems from the multiplexer. So here the figures are taken from the electricallyforyou.com, and problems we can see in the Packerly and tutorialfind.com. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.